Hello and welcome to Chemical Equilibrium. In order to have any sort of an equilibrium, a requirement is that we have something called a reversible system. So we have to have some sort of a process that's reversible. Reversible processes can be physical or they can be chemical. So the notes that we're going to talk about today are going to focus on chemical equilibrium. We're starting with a reaction here where we have SO2s and O2s. SO2s and O2s can react with one another and they can form and they can form SO3, okay? So one thing that can happen is SO2s can break apart and O2s break apart and they make SO3. And we actually talk about this particular reaction a lot because it's a really nice representation of a reversible chemical system. Because what actually happens here, okay? So in other words, what we're seeing is two SO2s break apart. So actually, I should say they pretty much stay together. This breaks apart. One of these will go here, one of these will go here, okay? So what actually occurs in this particular reaction is a couple of SO2s and an O2 make SO3. However, this is not something that stagnantly happens. This is actually a reversible chemical process. What I mean by this is SO3 can actually decompose, sulfur trioxide can decompose back into SO2 and O2. So this is what's called a reversible reaction because it can go in either order. Once you've made SO3, that's not a permanent product, and what you can decompose it back into SO2 and O2, and those SO2s and O2s can continue to form SO3 as well. So this is what we call a reversible chemical reaction. In a reversible reaction, reactants can form products, which can then form reactants again. Our forward reaction here is the reaction of our two SO2s plus our O2s making SO3. But as we mentioned, this can also be represented in reverse. Two SO3s can decompose back into SO2s and O2s. So when we want to write them together, we don't want to have to write all that stuff out all the time. You may have seen these little reversible arrows before. And some people ask, does it matter which you write on either side? It really doesn't. We just kind of go with what we're given. So this little symbol right here is the reversible reaction symbol. You can kind of think of it like two arrows going in different orders. And people just kind of chop the other little parts of the flags off the arrow to make it a little bit quicker. You can also show it this way as well. So in a reversible reaction, both of these things are able to occur. When we have just SO2 and O2, we're not at equilibrium. When we have just SO3, we are not at equilibrium. What's actually going to happen with a system in chemical equilibrium is we're going to have both of these reactions occurring at the same time. And because both of these reactions are occurring at the same time, check it out. We have SO2s, we have O2s, we have SO2s. We have all of these in the reaction vessel together. So neither of these things are happening in isolation of anything else. And we have a mixture of all of these things, of all of these reactants and products in our reaction vessel. So what it means to be at chemical equilibrium is the rate of the forward reaction is equal to the rate of the reverse reaction. Both reactions are continually occurring. This is dynamic. Neither one of them stops. But the rates of these reactions is what is extremely important. Now, there's a little bit of confusion as to what that means with concentration. So the rate and the concentration are kind of two separate ideas that we have to tie together. So this graph right here, if we started with only SO2 and O2, so in this particular reaction, we have SO2 and O2, and you can look at this on the graph. We're starting with SO2, SO2 here, and O2 here. We start with 0 SO3 in this container. So if we start with just those two starting reactants, what's going to happen, they're going to begin to react, and we're going to start to see some SO3. Now that SO3 is also going to decompose back into SO2 and O2. So the decomposition, the reverse reaction is happening here as well. However, all of a sudden around minute 4, you're going to notice that these concentrations are staying constant. So when we get to equilibrium, we actually know we're at equilibrium because our concentrations are constant. It doesn't have anything to do with where these graphs intersect. So our final concentrations of these for SO2, which is our red line, we end up at 2. molar. O2, we're ending at 1 molar, and SO3, we're ending at 8 molar. The reactions, as I said, are both continuing, but these concentrations are remaining constant. This is a dynamic changing system. If we ran this, so we were starting with just SO3 in this reverse system, we begin with this SO3 breaking down and making SO2 and O2, which we see we're starting with 0 of each of those down here. The SO3 is going to start turning into SO2 and O2. And then SO2 and O2 might react to make SO3, but what's important to realize here, we're looking at the same system with the same conditions. So what we're going to notice about our concentrations is that our SO2 ends up at 2 molar, our O2 ends up at 1 molar, and our SO3 ends up at 8 molar. And those concentrations do remain constant. So a typical thing that you're often asked is, at what time did this reaction get to equilibrium? And the answer is 4 minutes. We know that because that is where our concentrations become constant. Oops, I just really can't spell the word constant apparently. So that's a very important part of our equilibrium definition. Now, it's also important to remember this is dynamic. This does not mean that those are the same 8 moles all the time of SO3. It just means that as they're changing back in SO2 and O2, these reversible processes are happening at the same rate. So what I mean by this, I'm going to go back a couple slides. Oops, there's where I meant to be. This is not stagnant. So this SO2 right, or SO3 right here might break down and make these things, okay? Just because I'm seeing it at this one point doesn't mean it's going to stay that way. But every time one of these breaks down and does the reverse reaction, some SO2s and some O2s will react to have the forward reaction occur again and make more SO3 to replace that. So what we notice about the concentration of each component is they become constant at equilibrium. It is very important to note that they are not equal to one another. So concentrations are not equal to one another at equilibrium. No, these reactions have not stopped. Equilibrium is dynamic. At equilibrium, concentrations are constant. Concentrations constant. But these concentrations do not have to be equal. Now, you could have a particular system where they are, but that's not definitional, it's not a rule, and we usually don't deal with situations like that. One last thing I wanted to kind of wrap up before we go on to shifting equilibrium is that our concentrations are constant and our rates are what are actually equal. So saying I have concentrations constant, rates equal. I do have a nice animation for this I want to open up, so I'm going to pause for a moment and make sure I can get this. Upon going to that link, I found out that the file has been lost, which is a huge, huge disappointment. So I apologize for that. Hopefully we can find another simulation or animation to use.